take it away.
Awesome. All right, thank you, everyone. All right, so I'm going to try to pack a lot of information in a very short amount of time. I hear we only have about 10 minutes, so this is going to be pretty quick, but I'll try and work my way through it and kind of hit on a few major points around data and analytics. One of the reasons why we submitted this topic and why we want to talk about the importance of accurate data is most of the cities and engineering departments are making pretty large decisions off of data. We're making design choices that roll construction, we're building roads, we're building bridges, and using data correctly to make those decisions and understanding the data is very important. So we're gonna talk a little bit about how you look at data, how you verify its accuracy, and what does accuracy even mean. This is a very near and dear topic to Miovision. If anyone's familiar with Miovision, we are a video-based data collection tool set around counts, multimodal applications, and looking at how do we help facilitate accurate data and design around different modes of transportation, especially peds and bikes, one of the most challenging types of modes to actually collect. And so we collect across a lot of different intersections. We're about 100,000 intersections today, so we looked at a large set of data to really understand what does accuracy mean. Many vendors that have other tools often just say random statements like it's 98% accurate. But what does that really mean and how do you actually look at that data? And so just to iterate on that a little bit, we use a permanent base count tool set that looks at pedestrians, bikes, cars, trucks, everything that's in the roadway. And we look at wintertime, summertime, we look at different climates in northern Canada all the way to southern US. So we see a lot of different variability in what video data actually represents. And so we had to develop a system that actually looks at this data set and actually iterates on this data set. You're never going to get it perfect right out of the gate. So how do you actually create a system to iterate on it and take feedback, learn from the video itself, and create accurate data? And so we did a little bit of a case study when we built this platform and we built this tool to really understand what is our accuracy telling us and how are we going to make decisions from it. So we looked at 31 intersections from a major urban center here in Canada, where a large part of the focus was bikes. How are the bikes interacting with the signal? Are they going perfectly, turning left like the vehicles? Are they going through left? How are they interacting with the signal itself? How does that actually interact with the lights, the pedestrians, and the bicycles all at the intersection? How do you count that continuously from different angles from a single point camera and understand what that statement means of 95% accurate or better? And so here's a good example of how complex it can get when you're looking at a lot of variability within a video. So variability not just means different climates and different views, it also means different things happening simultaneously. Vehicles happening at the same time as pedestrians and buses and trucks, everything all together, and how do you minimize opportunity for variability in the data set? So we had to create an actual golden data set. You have to actually compare this to something. And so through our Scout product, which is a process that actually validates data, it's how we've guaranteed accuracy in our Scout product over the years to actually deliver on consistent data sets. We had to create a golden data set to actually compare data to see how it continuously operates. So painstakingly, we built this system to actually validate against and actually compare it to the algorithms running to see what the variability in it is actually occurring. So within the case study, we actually achieved some really high accuracies. We saw an error rate of 0.5% on vehicles and an error rate of about 3% on pedestrians. So to flip that, it's 97% accurate on pedestrians, very high accuracy. So what does that really mean? And we can unpack that a little bit more. So there's two major parts of how you view accuracy and how you actually think about the data set. There's the accuracy of how close to truth are you, so the difference between what the measured value was and the observed value. This is really looking at your statistical bias or your systematic error that's actually built into the system, that's actually looking at what is the difference between what you see and what you get, and measure that over a longer period of time. The second is precision, or in other words, variability. How often and how much do you deviate from that throughout the entire day? So that means, is it the same at nighttime? Is it the same at daytime? And is it continuous in all types of weather? And how do you reliably use that data throughout time? And so when you actually start looking at different percentiles or different variability, the 68th and 95th percentile data, you actually start seeing a whole different picture of what your data is representing. You're starting to look at 68% of the time, the error rate is within 4%, even though we saw on the previous slide that it was within 0.5%. And so you see a different picture when you look over a longer period of time. And so you see more of a distribution of error occurring throughout the day, not necessarily a single statement that you can make, which makes the problem a little bit more complex. And so to actually think about how to minimize this type of error, how to actually look at data, is look at longer data sets, look at different bins sizes. 15-minute bins versus hour bins of data set mean different things. Look at different times of day, look at different placements of where and how you're looking at the data. And you can even play the game of what statistics actually provide you. The difference of 1 out of 100 is way different than 1 out of 10, and making sure you're balancing the data sets appropriately. And so when you actually put it all together and you look at the variability, you see a much difference of a picture. You see variability throughout the entire day. You see some intersections throughout a larger sample set have higher variability than others. And so you want a larger sample set when you think about an accuracy statement and when you're making a decision off of the data. A single piece of data is not enough to represent the whole story. So you really have to unpack it and really understand the variability and how you can trust that data. One of the most obvious examples I can give in the short period of time that I have here is occlusion in video. If you have a scenario where there's high volumes of large vehicles like buses, trains, or trucks, they can create occlusion throughout the day with variability on them that one day may not look the same as the next day. And so looking for all these statistical errors and some random errors that are occurring in the data set will help you really understand how to make decisions from it, or put countermeasures like extra cameras or more visibility or more intersections and more collection to make sure you're making the right decisions. So I'll just conclude with that. I would encourage you to start asking questions about your data, prove that it's accurate, prove that you're getting what you're looking for, and that the decision that you're making from that data set is going to lead to the result that you're actually looking for. So thanks everyone. I'll conclude it there.
So I wanted to open up for questions first. Does anyone have any questions for Brent? While you're pondering that, maybe here's a question. I'm going to give you a tough one over here.
Oh no.
So as you're analyzing accuracy, and we talk about the overall accuracy, but usually most sensors of any sort, there's certain conditions where they're weaker. Did you see any parts of any conditions where that the Miovision system is a little bit weaker than other conditions?
Sure. One of the best examples of this is in the bike category. So one of the things that we notice pretty quickly is daytime versus nighttime and angle of the object itself. If you think about the way a bike looks head on versus the way a bike looks from the side you have the wheel and a frame and a person, and it makes sense. But from the front, it just looks like a person. And then when you add nighttime and daytime to that, then it is even harder to differentiate those features. So creating strategies of better camera placement and better lighting and better proximity to where you're looking at for the object was a big learning from the exercise of how just nighttime and daytime come into play on very small, vulnerable user objects in the frame.
Yeah, it's great presentation. We're doing a pilot project in a city in Metro Vancouver where we're monitoring vulnerable road users, and we're hoping to eventually get to a point where we can predict when an incident will occur before it does, and then intervene in some way. In other words, prevent the accident from happening. You can do that in a variety of ways. You can advise the vehicle, the VRU. You could extend, the green time or whatever. Do you see that happening more in the future?
Great question. Absolutely. The more we can have the system support the vulnerable users moving through the intersection and have it automatically account for it, you actually get closer to preventing an injury or a fatality. And so what we've been doing is making sure our accuracy is consistent enough that you can deploy an active version of instead of data collection, an active version with the traffic controller. And some of the things we've already started to do are like pedestrian extensions as an example. If you have large groups crossing the road, how do you make sure there's enough time for the large groups? Or if you have a bike entering the intersection, how do you extend the light? And now we're reaching a much higher accuracy on pedestrian and bikes from video that you can actually have that interact with the traffic controller and start making logical extensions or logical countermeasures from it. There's also tools like near-miss analysis that actually help you see where it's physically occurring, where is the conflicts occurring, and then build maybe physical countermeasures, not just active management through a traffic controller, and create a series of different countermeasures to improve safety across an intersection. I think video is one of the tools you can use to, one, actively manage it, and also assess where is it occurring, and then come up with what is the right countermeasure for the particular problem at that intersection.
The location and even a particular movement might be a critical thing that you could focus on. Yeah, that's
One of the biggest things that we've been seeing is the right hook across bike lanes, where a vehicle turns across it without actually looking in their blind spot properly when a bike is trying to cross. Even when signalized intersections are saying don't go for the bike often goes, and the vehicle is turning right. So there are some scenarios where if you collect enough data, what is the countermeasure to it? And we're starting to see a lot of great research in university of how do you countermeasure even when non-compliance of the signals are occurring. Signage, physical barriers, timing of when you're allowed to turn right and when you're not allowed to turn right. But all those are the right questions. So our goal is to get you the data of what is occurring, create a way to actively manage that, but give you the tools to help you figure out what the right countermeasure is.